welcome to another episode of The Dancing Professor. On today's episode, we're going to start focusing on the more cognitive aspects of human factor psychology, and we're going to begin by talking about memory. As you see from our overview, we're going to start by talking about sensory memory and how that leads into short-term memory. And after we figure out short-term memory, we're going to learn about the differences between short-term memory and working memory. After we talk about those three types of memories, we're eventually going to finish up our discussion by talking about long-term memory. So we're going to discuss the various models of memory that we have, and then we're going to wrap up this lecture by talking about memory and how it relates to specific parts of the brain. So those of you that were really interested in the neurological aspect, that's exactly what we're going to be talking about today. So first of all, let's define memory. Memory is defined as retaining, retrieving, and using information about a particular stimuli after the original information is no longer present. So if you're trying to remember something, or let's say you're trying to repeat something or memorize it and it's still in front of you, that is not considered memory. The important part of this definition is the fact that you're trying to retain this information after it is no longer shown to you. So in 1968, Atkinson and Shiffrin came up with the modal model of memory. And as you can see, it consists of a variety of different modes. So it's going to begin with sensory memory, and we're going to talk about this in more detail in just a minute. But basically, sensory information enters your sensory memory. It gets transferred to short-term memory. If you keep rehearsing it, right, it will stay in short-term memory. And after you encode it, it eventually makes its way over to long-term memory. If you don't retrieve the information from long-term memory, the information gets lost, also known as forgetting. But if you're actually accessing your long-term memory to retrieve things back into your short-term memory, that actually keeps the information stable in your mind. So that expression, if you don't use it, you lose it, is actually very true and very much so illustrated here. So we're going to talk about this model in specific detail, so here we go. So again, we discussed the definition of memory. Now let's talk about sensory memory. Sensory memory holds all incoming information for seconds or fractions of a second. So this is pretty instant, right? And sensory memory then relates all of that information into your short-term memory. Short-term memory, depends on who you ask, lasts between 15 to 30 or 15 to 20 seconds, but never anything drastically different from that. And we know that the capacity for short-term memory is about 5 to 7 items. After short-term memory, if it's been successfully encoded, it will be stored in long-term memory. And long-term memory holds very, very large amounts of information for a very long period of time. So almost if you think about it, sensory memory is fractions of a second, short-term memory is 15 to 20 or 15 to 30 seconds, and then long-term memory is everything past 30 seconds. So it could be 30 years or it could be 31 seconds, right? And that's unfortunately the not very clear definition of long-term memory. So if you recall when we met with our pilot, right, and we talked about multitasking, divided attention, and selective attention, we also talked about automatic versus controlled processing. So when we're engaging in selective attention, we're actually activating controlled processing because we're dedicating all of our cognitive resources to one particular task at hand. On the contrary, automatic processing is what occurs when we're able to multitask. For example, it doesn't require much processing on our part to be able to chew gum and walk at the same time. It doesn't require a lot of processing for us to be able to watch TV, or in this case, watch this lecture video and eat your food at the same time, right? So as we multitask, the task load becomes easier, right? In order for us to be able to in order for us to be able to successfully complete a variety of tasks at the same time, those tasks cannot be difficult. So if we were trying to multitask and each task required controlled processing, that would end up slowing us down and decreasing our efficiency. So in terms of memory, right, it's easier to remember to do things based on automatic processing, and when we actually have to try much harder to remember things, then that is more related to controlled processing. So the memory system, again, is involved in controlled processing. And one great example of that is rehearsal. Rehearsal is repeating a stimulus over and over to hold it in short-term memory. So there's a common misconception that if you rehearse something over and over, you're going to maintain it in your long-term memory, but that actually is not true. If you're rehearsing it, which means you're repeating it over and over and over, it's still living in that center mode of short-term memory. As soon as you stop repeating it, you can forget it, right? So that's why rehearsal helps you keep things in short-term memory. So let's talk more specifically about sensory memory. As we mentioned, sensory memory helps you retain information for very brief periods of time, right? And this is a result of sensory stimulation. So when we talk about senses, we have our hearing, we have our vision, we have our sense of smell, we have our taste, and we have touch. And I don't know, maybe someone out there has a sixth sense, but for the purposes of our lecture and of human factors research, as far as we know, we just have 5 senses. So my question for you is, which sense do you believe will have the longest retention? Which sense do you think helps us remember for a longer period of time? So we have iconic memory, right, or visual icon, which is the persistence of vision. So this is the retention of visual stimuli, and this lasts for less than 1 second. And an example of this is the flickering frames in a film. So I'm not sure if any of you have ever seen how old movies were made, but basically there are 26 frames that make up 1 second of a movie, of film. And so if you ever look at those old Mickey Mouse cartoons, you know you have to actually flip through the pages to see the motion. So in a sense, every time your eye catches something, right, every time a visual stimulus enters your visual field, your iconic sense, your iconic memory will remember it as little pieces instead of as one moving image. And the other one we have is called echoic memory, right? So if you think about echo, right, that means sound. So echoic memory is the persistence of sound. And this typically lasts about 3 seconds after the presentation of the auditory stimulus. So if you can think of an example of that, one example can be, let's say, you know, like delayed reactions when someone calls your name, right? Let's say you would be walking by somewhere and someone called your name, and a few seconds later, you may have still heard it. Or sometimes you're singing a song, right? Or you were listening to music as you were driving, and then the song had ended, you shut off your engine, you exited the car, but you could still hear that song playing in your head. So that is an example of echoic memory. And so to answer the question, which sense will have the longest retention, it is in fact echoic memory, not iconic memory. So what happens when we have no memory? So we know that we have these different types of memory. We have long-term memory, we have short-term memory, but we really take for granted our ability to remember things, and there are a variety of disorders and disabilities that come with memory loss, such as Alzheimer's and things like that. But we sort of only start to pay attention to that, as people start to get older. But things can happen, right? Hopefully nothing like that would ever happen to us, but there are things that happen that allow people, not at an old age, to lose their memory. So let's take a look at what it's like to live without memory.
One man is consigned to live entirely within the present, with terrible consequences. Clive Waring has the worst case of amnesia ever known. 20 years ago, he lost his memory, and now his wife, Deborah, is the only person he recognizes.
Clive really only has less than 30 seconds memory, and sometimes it's as little as perhaps 7 seconds. It's as little as a sentence.
I'm going to see your sister, Adele. Her daughter's got married recently in New Zealand. And so they're having a party.
Funny how the ladies acquire different titles when they get married.
Do you know who I'm going to see tomorrow?
Buckingham Palace?
No, really guess.
I don't know.
You don't know? Adele.
Oh, I see.
Do you know why I'm going?
No.
She's having a party at her house tomorrow.
It's her birthday, isn't it?
No.
No.
Do you know why?
No.
It's to do with her daughter.
I see.
Do you know why her daughter's having a party?
No.
Guess.
No idea.
She's just got married.
Oh, I see.
She just got married in, do you know what country she just got married in?
No idea.
In New Zealand.
Oh, I see.
The sentence he is in, he will probably have forgotten the sentence before. You ask him a question and he'll give you an answer, but while he's giving you the answer, he's already forgotten the question. That's how short it is.
I'm going to see your kids tomorrow.
You see my kids?
Yeah, your children.
What are they up to now?
Do you know what they're up to
No,
now?
no.
Guess what you think they're up to.
No idea, I couldn't guess. I don't know what their O-levels were. They hadn't got an O-level last time I was conscious. So I didn't know what possible thing they could do, did they?
Yeah.
And I couldn't possibly guess.
Where do you think they are?
No idea. Don't know where I am.
All he has is void behind him.
It's been like death. I've never seen a human being before. Never had a dream or a thought. The brain has been totally inactive. Day and night the same. No thoughts at all. As far as I'm concerned, the doctors have been totally incompetent. I've never seen a doctor the whole time. Oh, look, it's come.
That's a very musical kiss. I'm dizzy. I don't know which part of the room I'm standing in.
So yeah, that is the curious case of Clive Wearing, and as you've noticed, there are certain things that he does remember, but there are certain things that he doesn't. So Clive Wearing actually suffers from both retrograde and anterograde amnesia, which we will learn more about in our long-term memory chapter. So let's go ahead and continue with short-term memory. So we constantly use short-term memory by holding small amounts of information for very brief periods of time. So again, if you remember, the duration of short-term memory, as we mentioned, is 15 to 20 or 15 to 30 seconds. But what happens to that information after 20 seconds? Well, sometimes we forget this information due to what is called interference. So interference is a term that we use, in on a daily basis, and it's when there's some sort of an obstacle preventing you to get from point A to point B. So the same thing goes for information in our memory. If the point A is in long-term memory and we're trying to get it out of there to point B into our short-term memory, sometimes there are various obstacles that prevent us from doing that, and that is called interference. We have two different types of interference. The first type of interference is called proactive interference. And this is when something that you've previously learned before is interfering with information that you're trying to learn for the first time. So previously learned information is interfering with newly learned information. For example, let's say you have been living at a particular address for about 10 years, and then you suddenly got this amazing job, then you're like, hey, I'm going to go move, I'm going to buy a house, and you move and you change your address. But for a very long time, you still continue to write your old address by force of habit because that is what you remember. So that is an example of proactive interference, when information from the past is preventing you from learning something new. So if we have proactive interference, the opposite of that would be, of course, retroactive interference. Retroactive interference is the difficulty of recalling old information due to newly learned information. Excuse me. So let's say, going back to our house example, let's say you've finally memorized your new address, and then you decide to apply for a new job. And at this new job, you have to fill out this ridiculously extensive job application, and they ask you about all the different addresses that you've lived at in the past, 10 years. And so it becomes very difficult for you to remember your old address because you're so used to the new address. So in this case, the newly learned information is actually creating an obstacle between the older information that you already knew before. So that is retroactive interference. So proactive interference and retroactive interference, they both, interference, they both exist, and one is preventing new information from being learned, and one is preventing older information from being obtained from long-term memory. So basically, besides interference, right, if you don't successfully retrieve the information that you are looking for, or if you do not successfully encode the new information into your long-term memory, it eventually ends up in the trash, or meaning that it gets forgotten. So when we discuss long-term memory, we're going to talk about different ways to actually strengthen those neural connections in a way for us to reduce the amount of information that we forget. So how much information can we store in short-term memory? So capacity is the word that we use in human factors to describe the amount of information short-term memory can hold. The typical span is between 5 and 8 digits, or units or items. So Miller wrote this wonderful paper in 1956 titled The Magical Number 7. And his whole theory is 7 plus or minus 2, that humans in general can store 7 plus or minus 2 items in their short-term memory within those 15 to 30 seconds. So 7 minus 2 is 5, 7 plus 2 is 9. So anywhere between 5 to 9 items is what Miller argues is the capacity of short-term memory. And if we think about it, we can actually come up with some categories that include the number 7, such as a telephone number, right, without the zip code. Without the area code. We have 7 days of the week. We have 7 letters or 7, digits on a license plate. At least in America, we do. So there are a variety of different things that are categorized with the number 7, and it's very interesting to know whether that was done on purpose or not. So as humans, right, we're always trying to get things done more efficiently, to speed up processes, and actually to be able to remember more. So there are ways that we can actually increase the capacity of short-term memory. And one of those main things, again, as Miller coined, is called chunking. So a chunk is basically a collection of things, right, into one group, right? One basic mass. So chunking in the psychology terminology refers to combining smaller units, such as words, into larger, more meaningful units, such as phrases or sentences. So if we think about it, even letters grouped together, certain chunks of letters make up words. It would be easier to remember various letters within a word than it would be to remember the letters on their own. So this chunk, right, this collection of elements is typically strongly associated with one another, but it's also weakly associated with other chunks in the sense that you probably wouldn't confuse one chunk with another and actually decrease your ability to increase the capacity of short-term memory. So let's say if you're trying to remember song lyrics, right? Instead of trying to remember word by word, try to remember it as a sentence. And then instead of having the capacity of remembering 7 words, you increase those words into chunks of sentences, and therefore you can remember 7 sentences instead of 7 words. That increases your short-term memory capacity because you can imagine how many more words fit into 7 sentences than just 7 words alone. So any way that you can group and organize information that you're trying to memorize or trying to remember is actually a great way to increase short-term memory capacity. So coding refers to the way information is presented. Please do not confuse coding with encoding. These are two very different things. Coding refers to the process of moving information from sensory memory into short-term memory. Encoding, which we have not spoken about yet, refers to moving information from short-term memory to long-term memory. So in this case, coding has a physiological approach, right, when the stimulus is represented by the firing of neurons. So essentially, because information from the environment enters our sensory receptors, enters our sensory memory first, that is going to affect, again, those 5 senses that we talked about. And we have a variety of different neurons that are specific for reacting and for, perceiving different types of stimuli based on the senses that it's activating. Then there's the mental approach to coding, which is how a stimulus is represented in the mind based on particular experiences. So if you're sensing information from the environment, and it might be something that you've already known before, for example, if you've learned these things in an introductory to psychology class, then you would probably be taking a more mental approach to this information because it's something that you already know and you're able to apply it to previous knowledge. So auditory coding, right, related to the sense of hearing, can be the sound of a voice or a sound of a musical instrument, basically anything that you can hear. Visual coding is us using our visual cortex and our occipital lobe to be able to view stimuli as it hits our photoreceptors in our eyes. So anything image related would be visually coded. And lastly, we have semantic coding, which is understanding what is being said. It's understanding the meaning of words. So in this case, just even using this current setup as an example, auditorially, you are coding my voice and the things that I'm saying because you can hear me. Visually, you are coding the PowerPoint presentation, what you're seeing on your screen right now, and semantically, you're coding it because you're actually understanding, or you're hopefully understanding, the things that I'm telling you. So by combining the sense of hearing, of vision, and of comprehension of what is being said, that is a great way to increase your short-term memory capacity and to have successful coding from the environment, from the sensory information, entering your sensory memory, and eventually being stored in your short-term memory for those 15 to 30 seconds. So some evidence that we actually have a variety of different types of coding are presented here. So in 1964, a gentleman with the last name of Conrad conducted an experiment based on errors in auditory coding. So in his experiment, participants were presented with a series of letters. Then he asked participants to recall the letters in the order in which they were presented. And when they actually ended up doing that, the participants were most likely to misidentify similar sounding letters. For example, if the target letter was F, a person might identify the letter saying that it was S or that it was X. And if you remember, when we talked about aviation principles and our machines of war lecture, I actually showed you another example of research that actually helped invent the aviation alphabet, and why they did not use words like A or letters like A, B, C. Instead, they changed it to Alpha, Bravo, Charlie, Foxtrot, and so on and so forth, because over the radio, just the letters themselves were very easily confused. And so back in 1964, in psychological experiments, that was proven as well. We know that semantic coding exists because in 1976, Wickens and his colleagues conducted another experiment where they had 3 different groups of participants, and they were divided into 3 different categories. So one group received words in the fruit category, one group received words in the meat category, and one group received words in the professions category. So clearly there is one odd one out. After they heard these lists of words with their corresponding categories, they were asked to count backwards for 15 seconds, just as a distractor task. And then they were asked to recall the words 3 times. So what happened was, in the last trial, when all of the participants were presented with the fruit words that they had to remember, the people in the professions category did not experience any interference whatsoever because their category was so semantically different from professions. Fruits and meats are both in like an edible category, right? They're related to food. So they were more likely to make errors in the words that they actually saw. But people in the professions category that received no such words were much more able to successfully complete this task. And this just goes to show that even when we're trying to memorize a list of words without a lot of controlled processing, the semantic meaning of those words really plays a role in which information gets through and which one gets lost. So it's really important to sort of understand why there was this introduction of the working memory model, and how is working memory in fact different from short-term memory. So in the modal model that we discussed, where we have sensory memory, short-term memory, and long-term memory, that model made memory seem like it was simply a storage cabinet for information. It didn't feel like the information was very dynamic. And so people started asking, okay, well, how can you explain the phenomenon of multitasking? If you're saying that we can only store 5 to 7 items or 5 to 9 items of information within 15 to 30 seconds, how is it possible that we can actually be doing more than one thing at once within those 30 seconds? And so that led people to shift their idea from the short-term memory model and the modal model of memory into a more of a dynamic model. And that's how we started coming up with the idea of working memory. So Baddeley proposed the working memory model in the sense that it was a limited capacity system for temporary storage, but it also involved the manipulation of information for cognitive tasks such as learning, comprehension, and multitasking. So the thing that really sets working memory apart from short-term memory is the fact that it is not only a storage of information, but it also allowed for the manipulation of information for things to happen with that information instead of just remaining stagnant and getting lost or getting transferred to long-term memory. So working memory differs from short-term memory in two ways. The first way is that it consists of several parts, and we're going to talk about the three different parts that make up the working memory. However, short-term memory has always just been one part, just short-term memory, like one large file cabinet where we store a bunch of information. And the second way that it differs is that it involves this manipulation of information during complex tasks, during divided attention, during multitasking, whereas short-term memory only involved retaining information. So the three different parts of the working memory model include the visuospatial sketchpad, which is the place of the memory model that is responsible for holding visual and spatial information, right? So all of that iconic memory, right, would get transferred into the visuospatial sketchpad. The second part is the phonological loop, right? So phono means sound. The phonological loop dealt with things that we could hear. So sensory memory that was auditory and auditorily encoded, or auditorily coded, would be stored in the phonological loop. And then there was the third part, the central executive, which essentially was the boss. It was the referee that coordinated the activity between the visuospatial sketchpad and the phonological loop. And the other main job of the central executive is to actually retrieve information from long-term memory into working memory. So those are the three main parts of the working memory model. And again, that differs from short-term memory because short-term memory is just one unit. So here is a picture of what that might look like in case you are more of an iconic learner and you can remember a picture better than some words. So the phonological loop would be activated if you are trying to remember a phone number or a person's name, or you're listening to something that is being said. And from this, we have discovered the phonological similarity effect, which says that letters or words that sound the same may be confused. And again, we saw that in Conrad's experiment in 1964, and we directly see how that relates to human factor psychology and how that related to aircraft and pilot communication over the radio. So when we say words and letters that sound the same, we mean G, C, B, T, V, P. They all end with this E sound at the end. So if I were to ask you to memorize those letters all at once, it's very possible that you might make an error and substitute one letter with another that also ends in this E sound. However, if you take the list of letters F, L, K, S, Y, G, maybe the L, F, and S would be confused, but K, Y, and G, those sound completely different from each other, so you're less likely to confuse those. Additionally, studies on the phonological loop led us to identify the word length effect. The word length effect says that the memory for the list of shorter words is much better than for a list of longer words. So why do we think that this is? Well, for example, if you tried to memorize the words beast, wife, golf, dirt as your short word list, and then you try to memorize property, amplifier, orchestra, and gallery, which one do you think you would have an easier time remembering? Probably the first list of the shorter words that have just one syllable. And the idea behind this is that it actually takes more time to rehearse longer words than shorter words. So if it takes you more time to rehearse it, it means you're going to have less chances to repeat them. So for example, if you're forced to remember a list of words, and again, rehearsal keeps them maintained in your short term, or in this case, in your working memory, and you have only 10 seconds to repeat them to yourself, you can probably repeat the short word list a larger number of times in those 10 seconds than the longer list of words because it just takes longer to say them. They have more than one syllable. So how do we maintain information in working memory? Well, one interesting thing is that besides rehearsal, rehearsal also it doesn't always work. And there's a phenomenon called articulatory suppression. And this is when a person is actually prevented from rehearsing items because of some irrelevant sound or something else that is interfering auditorily. So for example, if you try to memorize something and in the background, like your little sister or your sibling or someone in your family is calling and nagging your name or saying da 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 or something like that, it becomes very difficult for you to continue your repetition and your rehearsal. And this actually reduces a person's memory span, and it eliminates the word length effect. So regardless if you're memorizing a list of short words or a list of long words, with articulatory suppression, that totally eliminates that effect. So to suppress something, right, is to sort of hide it, to bury it, and to articulate, right, is to make something understandable. So suppression in this case is a bad thing. And so by being overloaded in your phonological loop with other unnecessary sounds, that actually affects your ability, because it's putting too much stress on your phonological loop, to be able to repeat things successfully. And so, yep, as I just mentioned, this overloads the phonological loop and it prevents information from entering it, because the same part of the brain, the memory model, that is responsible for repetition and for saying words over and over is the same part that is responsible for coding auditory stimuli. So when there's too many things happening on the same part of the model, which is the phonological loop, it becomes overloaded and it stops working. So let's try something interesting together. Try to memorize the sentence below. John ran to the store to buy some oranges. All right, so think about that to yourself. Now, consider each word in that sentence and say yes if it is a noun and no if it's not a noun. So, John, noun, yes or no. Ran, is that a noun? Yes or no? No. To, is that a noun? Yes or no? So on and so forth. So go through the sentence again. It's in your mind. John ran to the store to buy some oranges, and identify whether each word in that sentence is either a noun. If it is a noun, you say yes. If it is not a noun, you say no. And just think about how you did. Now we're going to memorize this sentence. The bird flew out the window to the tree. And now consider each word in the sentence and point on your screen to Y if it is a noun and to N if it is not. So the, no. Bird, yes. Flew, no. Out, no. Of, no. The, no. Nest, yes. To, no. The, no. Tree, yes. So which one was easier for you? I'd actually be very curious to know your responses if you were following along and doing this with us. But ultimately, it would feel like one of them was easier. And the question is, why? So if you felt in your experience that it was easier to do the latter part of the experiment where you were pointing to a Y or an N, then that is probably because in order to perceive that picture and to use Y and N as sort of little icons, that's because you were using your visuospatial sketchpad for that. However, when we actually had to memorize the sentence, say it out loud, and then identify if it was a noun or not, that actually, again, is an example of us overloading that phonological loop and having to do two different tasks using the same part of the memory. Whereas here, you could recite the sentence using your phonological loop and graphically look at the image using your visuospatial sketchpad. So the third part of our working memory model is the central executive. So the central executive does most of the work of working memory, and it coordinates the phonological loop, which is what PL stands for, and the VS. It is not Vidal Sassoon, it is the visuospatial sketchpad. However, it is also acting as an episodic buffer between long-term memory and working memory. So this episodic buffer explains why performance and capacity can vary in either the phonological loop or the visuospatial sketchpad. So it's not a secret, and I'm sure you've experienced this on your own as well. Some people have better memory than others. Some people have better working memory than others, right? Some people are better able to adapt to various situations. Some people are able to multitask better than others. Even in the experiment we just did together, someone that you might have tried that experiment with might have had different results than you. So if it is in fact true that we all have the same parts of working memory, which are the phonological loop, the visuospatial sketchpad, and the central executive, why is it that human performance varies so much? And so later, after Baddeley had already coined the working memory model, they had added this idea of the episodic buffer, which in a sense is like a highway that passes from working memory to long-term memory and from long-term memory back to working memory. For some people, that highway constantly has traffic and is congested and information processing is slow, but for some people it's faster. So here's sort of an updated version. You have your phonological loop, you have your episodic buffer, and you have your visuospatial sketchpad. And so all of this information is controlled by the central executive, but now this episodic buffer is allowing you to link visual information, verbal information to your long-term memory. So now we're going to wrap up our lecture today by talking about memory and specific parts of the brain. So working memory can be disrupted by damage to the prefrontal cortex, because the prefrontal cortex is what actually regulates higher level processes such as cognition, thinking, critical thinking, decision making, logic, judgment, so on and so forth. And of course, whenever we receive sensory input from the environment, it hits our sensory memory, but essentially our prefrontal cortex is what helps us actually maintain that information and distribute it correspondingly to short-term memory and then to long-term memory. We also have connected areas in the temporal cortex which form long-term memories. So of course we have 4 different lobes of the brain, and not to say that each lobe of the brain is responsible for different things. It's just that we have, based on brain imaging scans, we can see various areas that are very rich and very heavy in very specific neurons that react to various types of sensory information. For example, we have the occipital lobe, which is home to the visual cortex that perceives visual stimuli, right? Graphics, images, things like that. We have the temporal lobe, which is most responsible for coding auditory information, right? Things that we can hear. We have the parietal lobe, which is mostly responsible for, spatial awareness, for our balance and things like that, and sensing pain as well. So anything related to touch, it activates the parietal lobe. And then lastly, we have the frontal lobe. So the frontal lobe is, again, most responsible for these higher level thought processes. So imaging experiments show activity in the prefrontal cortex during working memory tasks. So again, back in the early 1900s when brain imaging was not a possibility, but again, with these advances in technology, we're actually able to see which parts of the brain are activated when we're doing a variety of different tasks. So it also showed that there's activity in the visual cortex because this is the first area to receive visual signals. So my question for you is, does sign language activate the phonological loop or the visuospatial sketchpad? And on that note, that actually wraps up our lecture on sensory memory, short-term memory, and working memory. Please be sure to check out the next episode in the series all about long-term memory to further understand how all of these 3 types of memory eventually relate to the largest memory storage, which is our long-term memory. Thanks so much for watching, everyone. See you next time.